Once we have defined the structure, we can compute its optical response through the FDTD method. To do this, we need first to open the relevant tool, which is over there. When we do this, we get a window which contains several parts. On the right, we will have the discretized version of our structure. On the left, in the tree, we have the summary of all the parameters of the simulation. And at the top left, we have the kind of computation we want to run. In this case, we are going to focus on normal incidence simulations. That means that light will come from above the structure straight. So first, I'm going to load the structure that we defined, and it is done by a right click on the tree and charging the structure in there. When we click on OK, we get the discretized version of our structure, which is why we see the steps. So we don't have anything smooth like before. Of course, those steps are related to the discretization steps that we choose. So if I set it to 2 nanometers instead, I'm going to get something that is much smoother, but the discretization time can increase, so sometimes one might need to wait. So I'm going to set this back to 5 nanometers. Okay. Next, I'm going to change the name of this calculation and where it's going to output its data. So this is done over there. So I'm going to call this sphere test, for instance, so that some of the files will inherit this name. And I'm going to change the output directory to this one, which will produce the files in this directory. Okay. We are still not set in this case. So in our simulation, we have 3 materials. We have the ambient material, the particle itself, and the substrate. So we need to add materials and define them. So I'm going to add 3 materials first. The material 0 will refer to the index 0 when we define the structure and so on. Since we want the material 0 to be air, I'm going to leave this to 1. Then I'm going to change the substrate to 1.5 as if it were glass. And I'm going to set the material 2 to a fit of gold that comes with the software. So my materials are ready. Now I need to define the analysis spectrum that I want, and this is done over there. So we have 2 boundaries for our spectrum. We have the minimal value and the maximal value of the analysis spectrum. In this case, it's defined in the visible. If you want to change those boundaries, you can do so here. Here we have the number of points in our spectrum that we will analyze. So let's say 800, 801, for instance. Over here we have the polarization of our incoming light. In the TE case, the electric field will be aligned with the Y coordinates, while in the TM case it will be aligned with the X coordinate. Okay, and when we click on OK, we see the change in our tree. The last thing that we need to check is the boundaries above. So in the normal instance mode, the X and Y boundaries are assumed to be periodic, but we need to have PMLs above and below the structure. The PMLs have parameters that can be complicated. So in this case, I'm going to change the sigma value of the bottom PML a bit. It's very hard to define exactly what is necessary as parameters, so one needs to try them out and study a bit how those computations behave. Okay, so at this point we're set. We can save this. Okay, and we just need to run it at this point. So we just need to click on run, and a new window appears which contains the real-time calculation of the field. So we have the x, y, and z value of the field at the mid-plane of the window. So we have exactly the same thing on both sides of our calculation window. And here we have the number of iterations and basically the time left in the calculation. So it can take quite a long time. In this case, we only have a few iterations to run through. We have set this to 5,000, which might be enough or not. And as we can see, the field is oscillating for quite a while, so it might not be enough. In this case, we might need to change this value later. So we just have to wait a bit. A good way to know if a calculation is, well, not a good way, but a necessary way to know if the calculation is complete is that there needs to be no field in there. So on the left part mostly, because the right part is normalized, but the calculation will not be done if there is still field remaining in the window. So this is the most important point. If it's not checked, the one will see error in the spectra, there will be oscillations, and this means that one needs to increase the number of iterations. Okay, so we are almost done, so we are at 5,000 iterations. So before looking at the results, we need to talk a bit about the iterations. In this case, I've set it to 5,000 in a fixed case, so that means that the computation will run through all of 5,000 iterations. It's a bit hard to predict when it's enough, so there is an adaptive mode. The adaptive mode will look at a plane or several planes and try to check if the field is now stable, or at least if the Fourier transform of the field is stable. So we need to change which planes we want to analyze. So if I set this to both, it will analyze the top and the bottom plane of the calculation, and it will do this analysis on a specific spectrum. So this can be what we set in the incidence, but it doesn't have to be. And it will do so on a limited number of points. So for instance, here it will be 500 by default. And at a certain level, the level is basically the percentage that we allow the Fourier transform to derive. Okay, but our computation completed, and that means we now have a few files that have appeared in the directory. So the calculation is basically contained in this one, and there is a script that is provided to load this and turn it into something proper. So this script needs to be run through MATLAB, MATLAB will run it without any issue, but it can also be run through GNU Octave, and I think CLab will also be able to load this. So we just need at this point to run this script, and we will get the result of our calculations. So it's loading, and we will get two figures soon. Okay. So the first one in this case is just the reflection and transmission coefficients with respect to the field itself, so it's not very useful to most users. And here we have the same values, so reflection, transmission in power in this case, and absorption. Well, it can be absorption or it can be absorption plus diffraction. It really depends on the periodicity of the structure, but the last one is basically the losses as far as the transmission and reflection are considered. Also, it's not reflection and transmission in general, it's specular reflection and direct transmission. So this is a reflection that is for the light that is coming back straight from the structure and what is transmitted straight through the structure. So it doesn't take into account the diffraction in this case. And that's basically it for a simple calculation.